going to talk about, inside of circles, we're going to talk about chords, arcs, and central angles. Okay, let's start with a central angle. Okay, a central angle is from the center of the circle, an angle that is created by two radii. Okay, this is a central angle. All right. Let me change colors here. An arc is part of a circle. So this area in blue here is an arc. And finally, we have a chord. A chord is if you drew a line from one part of the circle to the other. That's called a chord. Some basic terminology. So, let's talk about chords and arcs. Again, a segment whose endpoints are on a circle is called a chord. Okay? PQ is a chord. Okay? Now, every chord has a related arc. In this case, we have arc PQ. You can see how you label an arc, use the endpoints of the arc, and draw a little curved line over top. Okay? Here's our first concept. Congruent central angles have congruent chords. So if I were to connect O to P and O to Q, this angle right here is a central angle. Okay? Every central angle, all right? If we have congruent central angles, and that means the arcs are congruent. So if I had another circle over here, and I know it's a really crappy circle. Here's P and Q again. Okay? This angle is the same as that angle. That makes PQ congruent to PQ. At the same time, congruent chords have congruent arcs. And at the same time, congruent arcs have congruent central angles. So one always leads to the other. And it's a cycle. Okay, so using that concept, here we have two circles, okay? And we are given that these two circles are congruent. Circle O is congruent to circle P, okay? That means they're the exact same size, they have the same radii, and we're given that BC, arc BC, is congruent to arc DF. So knowing that, congruent arcs give you congruent central angles, which give you congruent chords. And it loops back around and continues. So what can we conclude? From this diagram, I know we are given arc BC is congruent to arc DF. Okay? Now what that tells us, okay? Congruent arcs give us congruent central angles. So I know angle O is congruent to angle P. And congruent angles give you congruent chords. So I know segment BC, or chord BC, is congruent to chord DF. And then it loops back around. If you have congruent chords, then you're back to having congruent arcs, and so on. Okay, here's another example. Within a circle or in congruent circles, chords equidistant from the center are congruent. Okay? Second, congruent chords are equidistant from the center. So how do you apply that? All right? Let's talk about chords equidistant from the center are congruent. So if you look, I'm going to label this point out here S. Chord SR is 9 units away from the center. Chord PR, okay? Chord PR is also 9 units away from the center. So what that tells me is chord PR is congruent to chord SR. Okay, now I know this is cut in half here because it's tick marked, so I know this is also 12.5. And we're asked to find the length of SR. So that length, if I add those two together, since I know they're the same length, if I add those together, I would get 25. Okay, here's another example of that concept. Okay, again, chords that are the same distance from the center are equal, are congruent. Okay, and vice versa. If two chords are the same length, then they're the same distance from the center as well. Now, chord AB is congruent to chord QS. It's the same length because they are equidistant from the center. Now, chord QS is 14. That means chord AB is also 14. Easy stuff. Okay, a couple other concepts. All right, in a circle, a diameter that is perpendicular to a chord bisects the chord and its arcs. So let me draw a little diagram over here, okay? Get my circle tool out here. All right, so let me draw a little circle here. Okay, so in a circle, a diameter, so let me draw a diameter. Diameter goes through the middle all the way across. A diameter that is perpendicular to a chord. So let me draw a chord. Make sure it's perpendicular. So if that diameter is perpendicular to a chord, that means it bisects the chord, cuts it in half. Okay? Second concept, 11.7. In a circle, a diameter that bisects a chord, that is not a diameter, is perpendicular to the chord. Okay, so that is basically just the converse. It's the reverse meaning of the previous theorem. Okay? And the last one says 11.8. In a circle, the perpendicular bisector of a chord contains the center of the circle. That makes it the diameter. So basically, these all are just variations of saying the same thing. Okay, so we have two examples using that concept. Okay, so we're going to find each missing length to the nearest tenth. Okay, so here we have a chord LM. All right, now if you picture, this is technically a diameter if I were to look at it. Okay, now I know that that diameter is perpendicular to the chord, which means those are now equal. Now the whole thing is 14, so I know this is 7. Ln is 7, okay? So I'm going to take this triangle out of here, okay? It's a right triangle. This length is 3. This is R, stands for the radius, and this was 7, which was half of 14. So how do I find that missing length? Well, we're going to use Pythagorean theorem because we have a right triangle and we know 2 out of the 3 sides. So I'm going to use 3 as my A, 7 as my B, and the radius would be the C, which is the hypotenuse. So it's 3 squared plus 7 squared equals C squared. All right? And I'm going to do that math all at once. Okay? Square root of 3 squared plus 7 squared. Okay, if you do that correctly, the radius, which was R, is 7.6. And that should be bigger than the other 2 sides, and it is. Okay, let's do the same concept over here. Okay? Now, this chord is cut in half, which tells me the diameter that goes through it is perpendicular. So let me pull that triangle out of there. Our hypotenuse is 15, this length is 11, and we're asked to find y. So again, we're going to use the Pythagorean theorem. Y, I'm going to make my A, 11, I'll make my B, and the hypotenuse is C. So it's y squared plus 11 squared equals 15 squared. So that's, let's see, 121. 15 squared is 225. I'm going to subtract 121 from both sides. So y squared equals, let's see, that's going to be 104, and then square root 104. Rounding to the nearest tenth, our length here is 10.2. And that is a leg, so that makes sense because it's smaller than 15. Okay, here's an additional example. Again, the same concept, okay? So it says P and Q are points on circle O. The distance from O to PQ is 15, and PQ is 16. Find the radius, okay? So we're going to say, again, this is a 90-degree angle, which cuts that in half, which makes that 8. And again, we're going to use that right triangle that's in there. We have 8, 15, and we're going to find R using the Pythagorean theorem. This is A, this is B, this is C. So 8 squared plus 15 squared equals my radius squared. All right, I can cancel that out. I could do the math all at once. So we have the square root of 8 squared plus 15 squared. And I'm going to round that to the nearest 10. Actually, no need to round because this works out as an even 17. Okay, the next example deals with the same thing. Okay, you have technically a diameter here. If I were to extend that, it would be a diameter. So that means since it's perpendicular to the chord, it bisects the chord. So these are both 4. Okay, and we're asked to find that x right here. Now, x is a radius. Okay, now where it's drawn right now is not going to be helpful because it does not make a triangle. So if I took that radius and redrew it here, okay, all radii are equal. No matter where I draw a radius on this circle, they're all the same length, okay? So again, this is a simple right triangle problem. Pythagorean theorem. 3.6 squared plus 4 squared equals x squared. Cancel that by taking the square root of that. And I got 5.4. And that answer makes sense because it needs to be bigger than 4 and 3.6, and it